Okay, hello. Hopefully everybody's doing well. Today's a nice day out there, so let's get through this lecture and maybe go out and enjoy some of the sunshine. I think last time we ended up talking about motor action, and I went through, I explained in some detail the concept of motor action. I mentioned today, I mentioned that today I want to talk about the opposite of that. I call it generator action based on something called Faraday's law. So we'll delve into that. Before we get into that, though, I did mention a device called a railgun. And I don't know if you guys had a chance to look that up on the internet, or maybe you already know what it is. Now, normally, if we were face to face, there would be a series of videos I would show you demonstrating the Navy's railgun, and there's just a tons of railguns and railgun spinoffs out there that you can look at. I want to talk about it. I'm not going to test you over it. It's just this, it's interesting, number one, and number two, when I was in college, I had to build a small one of these and use that as my, what you would call my senior project, and do some calculations with it. So I just want to briefly kind of talk about how a basic railgun works. And it's kind of good because it gives us some practice using the right hand rule. So I want to talk about that. So basically, a railgun is a device that will fire a projectile, and it doesn't use any gunpowder, no kind of rocket fuel, none of that. It fires it basically using magnetism. So there's a lot of interest in it. I mean, you can imagine that if your ship at sea, you have a bunch of bombs and things of that nature on the ship with the gunpowder and explosive stuff. If there was a way to get firepower without having explosives, well, you can see why the Navy might be interested in it. And there's actually other applications that you'll come across. There's spin-offs of the railgun. There's one called a coil gun. And I actually had one of my UC students a couple of years back build a small coil gun, and it worked flawlessly. So basically, let me just talk about what it is. What I'll do is I'll give you a conceptual diagram, really simple construction of it, and then we'll talk about how and why it works. And then I want to go right into the main topic of the lecture, which is generator action. And there's a video I want to try to play. Now, this application we're using, I can share screens, and sometimes, at least the last time I tried to share a YouTube video, things got kind of messed up, so we'll see how that goes today. But there's one video I do want to show you to kind of lead off our lecture, and we'll get into Faraday's law. But let's talk about a railgun. And a railgun, to make a really simple railgun, you just need a couple pieces. So this is the top view of it. So it's like I got this thing on the table, and you're God, and you're looking down at this thing. So you get a big battery. Maybe like a car battery. And here are your terminals. And what I'm going to do is just connect a metal rod to each one of these. So I'm going to connect the metal rod to, I got a metal rod here. I got a metal rod here. And those are my rails. Those are the rails. So I'm going to connect the battery to these rods. And that's pretty much it. Just two rods connected to a battery. And then what we're going to do is take another rod and we're going to lay it across the two parallel rods, the tracks, or whatever you want to call them. We can see what's going to happen. If these are metal, they're conductors. When I lay this rod across the tracks, that's basically going to complete a path for current. So let's say I put this rod, the one that's free to move, let's say I put it right here. And so now what happens is current will flow through the rods. It'll flow this rod, back to the battery. Now these metal rods, you can imagine they're just like really thick wire. A rod is just a hellaciously thick wire. So that means you know from our studies that resistance of wire is rho L over So if I have a really, really thick wire, that means if this is really large, my resistance is going to be pretty low. So that means the current in that circuit, if this is really low because of my diameter of the wire, then the current's going to be really high. And remember, we talk about magnetic fields, electromagnetism. The definition of electromagnetism is magnetism produced by a current carrying conductor. And we said, or we mentioned that the magnetic field produced is proportional to the current. So this is used, then this is going to be used. So that's kind of some of the basic thinking. So what I want you to do is just kind of sketch this out on a piece of paper if you have one in front of you. But let's practice using the right hand rule. Use the right hand rule on each of the three conductors up there. And it's better if you have a coloring pencil or pen to kind of, see how things look. But if you have this in front of you, sketch this out on a sheet of paper. And if you remember how to use the right hand rule, apply the right hand rule to each of the three conductors, and let's see what your finished diagram looks like. I'll give you a second to do that. So while you're doing that, you remember that the way we're going to think about these magnetic fields. So if I have a bar magnet, and I got that flux coming out like that, and this is my eyeball, and what you would see is that the flux coming towards you. Or if I'm looking at the back of it, this is my eyeball, you see the flux away from you, so you'll see it like that. So one way to think about it is just an arrow, where that's the north pole and that's the south pole. So I'm going to represent that north with a dot, and I'm going to represent that south with a cross, like that. So we apply that thinking to this. Use the right hand rule in this conductor, on this rail. So the right hand rule says, remember, right hand rule, conventional current flow. My thumb goes in the direction of conventional current flow, and my fingers, which represent this magnetic arrow here, my fingers kind of come up and wrap around the conductor. So like I'm hitchhiking like that. And you can see at the top of that top rail, the north poles are coming out of the board, which means the south poles are going into the board. So to correctly draw those, we'll draw those like this. North's coming out, and here, south. And we do the same thing on the bottom, right hand rule, come that way. I reach in, I wrap around, my fingers are tips are coming out the bottom, so I got my north poles down here, and my south poles right here. Now right away I can pause for a second, and you can see a problem. The Navy, when they first built this device, well, first of all, they use typically they use capacitors, because what you want is a lot of current. And if you remember, you can get current from a battery. You guys studied cold cranking amps. In the car, when you turn it over on a cold day, those cold cranking amps, you guys researched that for me. You can get a surge current, but nothing like the surge current you can get from a capacitor. You can get a huge amount of surge current from a capacitor. We did a calculation the other day, a few videos back, where we looked at the surge current of a capacitor, and it was, I think we charged it. The max charge current was like 9 milliamps, and the maximum discharge current was 90 amps, so it was like 10,000 times bigger. So typically you would use a capacitor for this to get the surge current to give you a bigger oomph. But one problem is that you got these south poles here in the middle. So when they started experimenting with this in the beginning, the thing actually blew itself apart because there was such strong opposing poles between the rails. And if you actually go, like, there's a couple iterations of it. The Navy has, the one they use now looks ultra modern and sleek and all of that. But the one, when they first started experimenting with it, looks like kind of really archaic, kind of Frankensteinish. And you'll see that they have these huge bolts, really thick bolts and nuts and bolts, every couple inches to keep, because this thing it has to take so much force, so much magnetic force. So, but the magic happens when you apply the right-hand rule to the part that can move. So we got these tracks, these rails fixed, so they can't move. But this is free to move. When I lay that bar on here, let's see what the magnetic polarity looks like around the part that's ready to move. So if my thumb is in the direction of conventional current flow, you see my fingers coming out of this. So the north poles are like over here. And I got a south pole here and a south pole here. Now here's where the magic happens if you look at this. I got a south against the blue south here and a south against the south. So I got these huge opposing poles not balanced by anything over here. So there's a net force, a gigantic net force on this projectile to move that way. And this thing will like fly off the track. Now this is a really simple-minded diagram. You can, like I said, go to your videos, YouTube, and type in railgun if you're interested. I know I was talking to somebody at the end of I think it was Dave. We were talking, chatting at the end of the video, and he knows a lot about railguns, and he's adding copper to it and different things, which you'll see different spins of this. And it's kind of interesting, and it doesn't take a whole lot of like basic physics to understand how the thing operates. Now, basic physics, understanding how it operates, and engineering, building it, well, that's two different things. They ran into a lot of problems trying to build it, and as you see, they pretty much perfected it, and it actually they have these in operation. The Navy does, and probably, I'm sure, in other places that we don't know about, don't talk about. So that's the railgun. Anybody have any questions or comments on the railgun before I move on to the lecture? Well, if you get a chance, YouTube railgun, you'll get 1 trillion videos back. The Navy will come back. You'll be really impressed with the Navy railgun. And then you'll see a whole lot of spin-offs where people have made versions of this. And there's a spin-off called a coil gun. People have made actual handguns, coil magnetic handguns. So you'll see that. So if you get a chance to look at that, look it up. And I'm not going to ask anything about this on a test or quiz. This is just for personal interest. All right, so this next concept to me is, the most important thing we talked about all semester, believe it or not, Ohm's law. Because without that, you can't do any of this stuff. Second to that is probably, in my opinion, the other professors would argue, but in my opinion, would be Thevenin's theorem and maximum power transfer. And if you take me for AC, we'll come back and we'll apply that Thevenin's theorem and max power transfer. We'll apply that in the AC situation in some ways that I think you'll be really interested in. But next to that is this law that we're going to talk about, Faraday's law. And I'm going to talk about Faraday's law by attempting to show you a video, a YouTube video, and then we'll talk about the law. And if you take me for AC, I actually start with this video. The first day of class, I play this video for you, and that's how we start the course. Because this is the link between AC and DC in my mind. So now I don't know how well this is going to work, because like I said, I tried this before, and it didn't work out too well. But I found out my nephew was upstairs. I'm pointing up. I'm in my basement. And he was playing, I guess you can play those video games online. He has a PlayStation. And while I was using this Collaborate, he was using the PlayStation online. And I was wondering, why am I having all this just all kind of problems? And I just kind of, so the bandwidth for probably the bandwidth for this application we're using is huge. I'm sure the bandwidth for the PlayStation was used, so they kind of interfere with each other. But right now he works at a donut shop, so he's baking donuts. So I'm in the house by myself. So we'll attempt to show this video and hopefully it plays. So I'm going to try to share it with you. And if you don't see anything on the screen, let me know. And you guys got to talk to me now, because once I do this, I won't be able to see any of your little icon things. So I'm going to change my tab here. I'm going to try to share it with you, and I'm going to try to play the video, and you let me know if you can see and hear it. Let me figure it out here. This is the time my laptop was on really slow. All right. What are you guys seeing right now?
Still the
You
board.
seeing anything? You still see? Okay. Only part of
There you go. We see a screen now.
uh, you see the video, or you see your screen?
We see your screen.
Yeah, the Blackboard Collaborate screen from your view.
You don't see the video yet? What else you guys see? Well, let me see. Can I do this again? This is the only part of this application. I mean, I think the idea is really good, but okay. Let me try this. If I go YouTube, share application, share application. All right. All right. We All right. I don't know if this is gonna work. I'm kind of pissed off. That really, I don't like this.
Well, you know, when you're dealing with technology, you just gotta get stuck with it, and you know, when you get unstuck.
And get unstuck is when you. But you know, I just think it doesn't. And I'm seeing two. Okay, let me try something here. So you see the screen there?
Looks like we're back to the whiteboard.
Let me stop sharing. Okay, back to the. I'm gonna try one more time. If it doesn't work, I'll just have to. I don't know. I'll just have to explain it. But guys, demonstration in the video. Let it reload. It's loading. It's slow, and I did. After you walk in too, so hopefully it doesn't turn. And I even have a hard line. I'm not using wireless. I actually ran a line down directly to the computer for speed. And paying $80 for that, and this is what I get. And now it's just let me try one more thing. Close that. Go back to it. Uh, you're still reconnecting. Okay, you see the whiteboard now?
Yeah.
All right. Well, I'll tell you what I'll do. I'll put a link out. Oh man, that really upsets me because I really, guys, wanted you to see the video. I'll have to put a link.
If you want us to watch it now, you can put the link in the chat.
What'd you say?
I said if you're wanting us to watch it now, you can put the link in the chat.
Okay, why don't I do that? Let me see if I got the link. I tried to copy it, but who said that? That's a good idea. Who gave me that idea? Who was it? You don't want to own up to it?
Is it okay? It was Ethan, me.
Okay, Ethan, you don't have to take the final exam. You get an A for course. The other guys will have to take it. I like that idea. I just hope I copied the link. Let me try it. So slow. I might have to reboot this, guys, and see. I'm not. I mean, my whole system's like. Now I'm clicking in the chat box and nothing's happening. So let me do this. Sorry, I'm gonna disconnect for a second to try to reboot. I'm having some kind of issue that I'm not liking. So it just went to okay. I'm gonna disconnect and reboot. So I'm gonna stop recording and I'm gonna try to rejoin.